So thank you very much. So thank you, Jonas, for the opportunity to be here. And I would also like to thank SPIE, who actually is covering my my travel here. So I will talk about silicon nanocrystal as enabler for silicon photonics. But before of that, I would like also to show you where I'm coming from. So I'm coming from Italy, so Italy in South Europe. And Trento is a town exactly in the mountain region. So the weather conditions are more or less like here. We do have more snow too. Anyway, so the idea of this talk is to firstly motivate the reason why we want to develop a photonics in silicon, and then I would like to show you how it is possible to enable more functionalities in silicon by using low-dimensional silicon, so silicon nanocrystal. And so actually, this morning there was a claim that you want to change the physical structures of silicon without affecting the electronics properties of silicon. This is not what we want to do in this work. So what we want to do here is actually try to change silicon and make silicon what silicon is not thought to be able to do. Typically, you think about silicon for microelectronics, and you don't think of silicon for photonics. And this is actually what I want to convince you that indeed. So silicon is good for microelectronics, but is also good for photonics as well. So this is more or less the outline. So motivational silicon photonics. I will try to explain what silicon nanocrystal are, and then I will show you a few examples of devices that can be enabled by using silicon nanocrystal. So I will show photovoltaics. I will show light-emitting diodes. I will show a device for safety and secure communication. And I will show some nonlinear optical properties of silicon, and then I will draw some conclusion. So let me start from silicon photonics and what is the real motivation behind silicon photonics. So this is the real motivation behind silicon photonics. So this is a forecast on how big is getting actually the internet and the fact that we do want to have devices that are all the time connected. So as you come here, so the first notice that you get is the password to connect to Wi-Fi. So you want to be all the time connected. And here is an example of the consumer that are planning to purchase different devices. And what you see here is the fact that this ambition to be connected, to be all the time networking with friends is not only limited to the more standard technologies like smartphone or to laptops or to TVs, but now it's really entering everything. So we want to have a smartwatch, we want to have a fitness monitor, we want to run and then exchange with our friends that we run that distance, and so on and so forth. Actually, last year, Mark Zuckerberg wrote a message on Facebook saying that he is extremely proud because that specific day, more than 1 people over 7 in the world was connected to Facebook. So this is the kind of interconnectivity that we have. And so he was claiming that this is the beginning of a new connecting world. And he was also claiming that due to the fact the world will become better than what we know nowadays. So from a scientist, this means that the quantity of data that are exchanged through the internet is extremely large and is exponentially growing. So here is the bytes that are exchanged per month versus the years. And what you see is the fact that in the period 2012 to 2017, so the increase in the amount of traffic was more than 66%. And nowadays, we do exchange more than 12 exabyte of data per month. Actually, those data are the data that runs on internet, but there is also a location where the quantity of data that are exchanged is going to be much larger than those numbers. And this location is within the data centers. So we do think that internet is only associated with our devices and the connection of the device together. But this is not true because everything, all the traffic, runs through data centers. And nowadays, the real Earth of internet is at that level. And what is even more surprising is the fact that the amount of data that is exchanged is much larger within the single data center than between data centers or between consumers and the data centers. So here are the numbers, and what you see here is that the traffic from the data center to the user is only 25% of the overall amount of data exchanged within the data centers. So the data exchange within the data center are in the order of 24%. So the real Earth of internet, the real Earth of nowadays communication society is within the data center. So we do really have to care, we do really to be concerned what happens at that level. And so according to you, what is going to be what is actually the main limitation of internet? So you know what is the very single aspect of internet that is posing a huge problem that we have to solve? Question for the audience. Anyone has an idea? So what is the main problem with data center? So I have 1 hour waiting. Yeah? You know the answer. Okay, so he is correct. So this is good answer. So when you do a single search on Google, or when you exchange a message, or when you look at Facebook, or whenever you access to internet, you think to do something that is environmentally friendly. So this is called the green economy. So we do not make meetings and we use Skype. And so we do think that we do not consume. But this is not true. So each time we do a Google search, so we do consume a power equivalent to turn on a light bulb for 70 seconds. So when we do look in the smartphone, a video or on your tablet or whatever, and we look for 1 hour each week, so we consume more than a new refrigerator. So this is actually a big problem. So the problem that in the data center, most of the power is consumed to cool down the servers. And the reason is because microelectronics, microelectronics is associated to a flow of charges, and then you have the Joule effect. Joule effect means heating. And this is the issue. So we do really eat a huge quantity of power. When we do think to data centers, so the typical vision we have is this one. A clean, servers, everything proper. But indeed, so what we have to consider is that on the basement, so there is a huge part of the basement that is devoted to the cooling system, to the exchange of refrigerator liquids, to the dissipation of the power. So this is an example of a Google data center. This is a bike, just to give you an idea of the dimension of the problem. And it is even worse if you look at the data center as a placement. And what you see is that all those stuff needs only to provide power to the data center. And then here you have a very large cooling towers. So this is an issue. And this issue is associated to the electrical exchange of data. And so a solution, and actually this solution is to try to move light, to try to use optical communication within the server. In order, you want really to use light in the inter-server, within the server, on the board, within the board, in the chip, within the chip. And the reason is very simple, because with light, you do not have the problem of Joule heating. So this is the solution that we are looking at. And in order to do that, if we want to really have a technology that can be deployed without increasing dramatically the cost of the system, so you have to go to silicon. So you have to develop a photonics, meaning a technology that uses light to exchange data by using silicon. And this is silicon photonics. So actually what you want to do is that you want to integrate by using the very same concept that we had with microelectronics. You want to integrate all the different optical functionalities on a chip. So you want to make a silicon photonics chip that is exactly the equivalent of a microelectronic chip. And you want to do that by using the standard silicon factories. So you do not want to change your manufacturing, you do not want to change your industry, but you want to use the very same industry that you use to make microelectronics to make also photonics chip. And you want to do that because in this way you can leverage on the success of the microelectronic industry. That means mass manufacturing, that means low cost, that means high volume, that means high performance, as well as you want to use silicon because by using silicon you can naturally merge data communication with data computation. You can naturally merge computing or electronics and photonics, which means computing and communication on the same chip. So this is the evolution of silicon photonics along the timeline. So everything started in the 80s, 90s, and then we observe a very large improvement in the development of the technology. So we passed through the basic steps, the demonstration of the different components, and nowadays we are on the verge of a very large integration scale of photonic devices. So where are we? I just simply want to show you a couple of examples. One where I am personally involved. So this is a research where we want to develop a silicon photonics-based optical network on a single chip. So here is, I do not enter in details. So this is the network that we do integrate on the chip. So here we have more than 1,000 photonics components integrated, more than 2,000 electronics components integrated that are used to drive the single photonics component. So here is just to show you that is actually something that we do, manufacturers that we do fabricate. So here is simply the design, so the schematics, so where you see all the different photonics components integrated, and then here you have the input ports. And what I want to underline here is the fact that, so the dimension here, so you see is a huge dimension with respect to the standard chip. And the reason why here is so large is because optical fibers are enormous with respect to the typical size that we use in silicon photonics. So in silicon photonics, we are in the nanometer range scale, while optical fiber are in the micrometer range scale. Anyway, so this is the kind of chip that we developed. So a true optical network on only 1.2 centimeter wide chip. Everything is well scaled, and the cost is significant, is very low. So the overall cost of the optical network on the chip will be a few €100. So this is the possibility of silicon. Silicon means low cost if you do mass manufacture. And what you have on the chip is that you have 48 different optical channels with several directions and so on and so forth. So this is what we are doing in my university within a European project. And this is what IBM is doing. So also IBM is working. So IBM nowadays is selling silicon photonics chips, or Intel, two big microelectronics silicon companies, IBM, Intel. So Intel is selling what is called an active optical cable. So what they did was to put a silicon photonics chip at the end of an optical fiber. And in this way, so it is possible to make an optical cable. And so you can use this optical cable to connect different servers. And what you get with respect to electrical cable, so this is electrical cable, this is optical cable. So what you get here is at a much large bandwidth. So you move from 120 gigabit per second to 1.6 terabits per second on a single cable, as well as you get a much longer span. So here you can send a few hundred of meters far away without any attenuation in the signal, while if you use electrical interconnect, so you have only to you reduce the data rate as well as the span, so very shorter distance. Anyway, so this is silicon photonics. So silicon photonics nowadays is a technology you can buy products. So then what can we do? Okay, so this is the facility we have in Trento. So what we can do? So the title of my talks were using silicon nanocrystal to enable new functionality in silicon. And so why do we need to use silicon nanocrystal then? So because there is a fundamental limit in silicon, which is associated with the band structure of silicon. So we know that this is a textbook, a graph. So we know that silicon is an indirect band gap semiconductor. So indirect band gap semiconductor means that the top of the valence band is not at the same point as the bottom of the conduction band. So if you want to move one electron from here to there, you have to conserve the energy as well as the momentum. And in order to conserve the momentum, you need the assistance of a phonon. So the phonon has to take the momentum so that you move the electron from here to there. Otherwise, you cannot recombine. And this is the big difference between silicon, which is an indirect band gap semiconductor, and 3-5 semiconductor that are direct band gap semiconductor. So if you want to make a laser, you use a direct band gap semiconductor because in the direct band gap semiconductor, the direct transition, so the recombination between electrons and holes, is very easy. In silicon, it's not. So this is a big issue here. Because if we have an indirect band gap semiconductor, it means that the electron-hole pair have a very low radiative recombination probability. So that means that they have a very long radiative lifetime. But actually, this is not a true problem, because we have systems which are characterized by a very long radiative lifetimes with which we can make a laser. For example, the erbium-doped fibers. So we do buy erbium laser in fibers. What is really, and the lifetime of the metastable state in erbium fibers is 13 milliseconds, which is more or less the same as in silicon. What is the problem with silicon? Is the fact that silicon is a semiconductor. So the holes and the electrons do not wait 16 milliseconds there. So they do move in the semiconductor. And while they move, the probability to find a defect, a non-radiative recombination center is high. So they do prefer to recombine with non-radiative recombination, so without emitting photons, than with emission of photons. And this is the real problem. And this is the reason why in silicon, when we do excite, in order to have one emitted photon, we need to excite 1 million of electron-hole pairs. This means that the internal quantum efficiency in bulk silicon is extremely low, 10 to the minus 6. Gallium arsenide, typically 50%. So you excite 2 electron-hole pairs and you get 1 photon out. Here, we need to excite 1 million of electron-hole pairs in order to get 1 photon. And so here, low-dimensional silicon can provide a system where we can beat this indirect band gap of silicon. So we want to change the properties of silicon by simply reducing the dimension of silicon to small nanocrystal. First of all, so we see that the typical electron wavelength in gallium arsenide is 25 nanometers, while in silicon is only a couple of 5-6 nanometers. So that means that if we want really to beat the indirect band gap of silicon, and we want to enter in the quantum confinement regime, so we need to make this silicon so small that the electron de Broglie wavelength is similar to the dimension of the silicon nanocrystal. So we have to reduce the dimension of the crystal to a few nanometers. And this is what actually we are able to do. So this is a piece of amorphous oxide, silicon oxide, where we have formed a silicon nanocrystal. So you see all the lattice plane here. So this is a TEM image. So we do see all the lattice plane there. So here is this is a blow up of this. Here the length scale is 50 nanometers, so we can make many of those nanocrystals. So it's very easy. And what you immediately notice is the fact that now if you take those nanocrystals, you disperse in a colloidal suspension, and then you expose this colloidal suspension to blue light. And what you see is the fact that now this suspension glow in the red. So here you see two facts. The first one is that it's glowing. So by reducing the size of the nanocrystal, it is possible to get a quite efficient emission of light from silicon. Efficient. LED, blue LED, strong light emission. And the second fact is that the band gap of silicon is changed by reducing the dimension of the silicon nanocrystal. You see that the emission is in the red. So you are able to see, to observe. If you do not change the band gap of silicon, so silicon has a band gap of 1.1 electron volt, and you don't see anything. Even though it's emitting light, you don't see because your eye is not able to see. And so here you see the fact that by using this low nanocrystal, so it's possible to push silicon into quantum size effect, and so you drastically change the electronic properties of the carriers in those silicon quantum dots. So the first one is quantum confinement, so you reduce the size of silicon, and as a consequence, you increase the band gap of the material. And here is a plot of the transition energy, so the fundamental band gap, as a function of the diameter of the nanocrystal. You see that as when we do enter in the low, in the few nanometer region, so the band gaps increase, so you have a widening of the band gap, and then you drive the band gap into the visible range. So this is the first consequence of quantum confinement. The second consequence on the quantum confinement is the fact that now you squeeze in the real space the wave function within the nanocrystal. So the electronic and the whole wave function within the nanocrystal. But the Heisenberg principle tells you that if you reduce the in the real space, if you do reduce the wave function in the real space, you broaden the wave function in the momentum space. But broadening the wave function in the momentum space means that now the overlap between the electron that is confined at the X point of the Brillouin zone and the holes that is confined in the gamma point of the Brillouin zone is increased. So as a consequence, the radiative, direct radiative recombination probability is increased by the quantum confinement effect. So the more you confine the free carriers in the space, the larger you get the widening of the wave function in the K space. So you increase the overlap between the two, and so the radiative recombination probability increase. Now the radiative lifetime moved from the 10 millisecond typical of silicon down to the microsecond that is typical of silicon nanocrystal. So you get a widening in the transition energy, an increase in the radiative recombination probability. And then you get a third effect that is associated to the fact that now in the nanocrystal, the electrons are no longer free to move. And so this is what happens, as I already told you before. So if you take a bulk silicon, you have your electron-hole pairs. So they do move. They do not wait 13 milliseconds before combining, emitting a photon, because they do find radiative, non-radiative recombination center. And so you kill the luminescence because of the free movement of the electron-hole pairs. And this does not happen for electron-hole pairs in silicon nanocrystal. Because what happens now is the fact that now you do excite electron-hole pairs, but they are confined in space. So they are no longer able to move. So either you get one defect in the nanocrystal, so the nanocrystal is completely dark, or you don't get the defect in the nanocrystal. And since you do not have defects, so they do stay there and wait to recombine radiatively. So now in this example, I do have excited 3 electron-hole pairs, and I do get 2 photons out. So that means that this system here has a very high internal quantum efficiency because of the reduced non-radiative recombination caused by localization of the electron-hole pairs. So the example here is of a system that has an internal quantum efficiency of 66%. Good. How do we make those nanocrystals? Very easy, very simple. So what typically you have to do is that by any means, you have to form a substoichiometric silicon oxide. So you have to form, to deposit, to implant, whatever you want to do. You have to make a glass, a silicon oxide, with excess silicon, with some more silicon. So you form a substoichiometric silicon oxide, or a silicon-rich silicon insulator, silicon-rich silicon oxide. And you can use ion implantation, sputtering, chemical vapor deposition, or more exotic technique. So once you form this silicon-rich oxide, so then you simply anneal the film. And since silicon and silicon oxide are 2 different materials, they do prefer to separate. And so you have a phase separation within this silicon-rich oxide, and you have on one side the growing of silicon, and on the other side the growing on silicon oxide. Now you stop the annealing at the very initial phase of this separation. And so what you end up is that very small nanocrystal in the silicon oxide. And you can control the dimension of the silicon nanocrystal, so the dimension of the silicon nanocrystal, by the annealing temperature or by the annealing time. So here is an example of the emission wavelength of several silicon nanocrystals as a function of the annealing time for different silicon content in the film. So you increase the silicon content, and so you grow larger nanocrystal. You increase the annealing temperature, and so you grow larger nanocrystal. Larger nanocrystal, less quantum confinement, more blue shift in the luminescence. And so you see that the peak of the emission, so here is in wavelength, inversely proportional to the energy, shift to the red, caused by the fact that the nanocrystal grow in size. One problem with this self-aggregation of the nanocrystal is associated to the fact that you do not control precisely the dimension of the nanocrystal. So what happens is that they do aggregate, they do form, but you have a huge size distribution in the nanocrystal. And so here is an example of the typical size distribution that you get in your field. So the average size is growing when you grow the annealing temperature, but even though the average size is growing, you have a quite large size dispersion. So this can be an issue for some kind of application. However, it was demonstrated, and the fact that if you constrain now the growth to a specific layer, you can control the size of the nanocrystal. So the idea is the following. So you deposit a multi-layer structure of silicon-rich oxide, silicon oxide, silicon-rich oxide. And then you anneal. And it happens that the silicon do not want to enter into the silicon oxide. So the growth of the silicon nanocrystal is confined to the layer where you have deposited the silicon-rich oxide. So now the size of the nanocrystal is determined by the thickness of the silicon-rich oxide that you have deposited. And so in this way you can control the thickness and the size of your nanocrystal. And you no longer get a broad size distribution, but you get a controlled size distribution of your silicon nanocrystal. Here is an example. In this case, so the thickness of the layer is 5 nanometer, which means that the nanocrystal now have a size, a typical size of 5 nanometer. Good. One thing that is even more interesting as a result of the quantum confinement is the fact that by using silicon nanocrystal, it is possible to get not only emission, luminescence, from the silicon nanocrystal, but also stimulated emission, so gain, optical gain in the silicon nanocrystal. This is what we did in order to observe the optical gain. So let me talk about this experiment that is much easier to understand. So here is a transmission spectrum. So we have a film of nanocrystal on top of a quartz layer. So the quartz is transparent, so most of the light is going through. You get the absorption in the nanocrystal. But since the quartz and the nanocrystal have a different refractive index, when you measure the transmission versus the wavelength, you see an interference fringe. You see that you have absorption because the transmission is lower than 1. So this is a typical semiconductor. You take a film, you transmit some white light, and you know that some light is absorbed. And since the thickness is small, you get interference fringe. Nothing specific, nothing particular here. However, now, if we use a blue laser is something that is absorbed by the nanocrystal by promotion of one electron from the valence band to the conduction band. Now, if you pump with the blue laser, so you observe that the transmission is affected by the power of the pump, and then by increasing the pump power, you excite more and more electrons up to a level where you get population inversion. So you have more electrons in the conduction band than in the valence band. You have population inversion, so you can get a gain from the nanocrystal. And indeed, if you look at the intensity of the transmission, you see that the transmission is larger than 1. So it means that the signal has been amplified by the nanocrystal. More light out than what you get in. Where is coming the difference is coming from the blue laser, clearly, from the pump laser. So this is very important. So this is a result that is quite interesting in terms of the use of the nanocrystal to make a laser, because the first requirement for a laser is to have a material that is good to amplify light. Laser means light amplification, so you need to amplify the light. And so this is a good material for doing that. Here is an example that shows you that you have a gain peak at a certain wavelength region, and then this is the black line that shows the absorption. And so if you look at those spectral dependence of the emission, the absorption, and of the gain, naturally you end up with a model for the gain that is a 4-level model. Because it's a 4-level model because you see that the absorption is spectrally separated from the gain. So that means that what you absorb is not what is giving you the gain. And so this is the model that we have developed in order to understand the physics of the gain in the nanocrystal. And actually what we do observe is the fact that the gain is actually associated to interface states that form on the interface between the silicon nanocrystal and the silicon oxide within which the nanocrystal are formed. There you form some specific bonds between silicon and oxygen, and what happens is that if these bonds are excited, so you get a different separation between silicon and oxygen, and so now you are on these energy levels here. So here, this is the ground state of the silicon oxygen, and here is the excited state of the silicon oxygen interface state. And what you observe is indeed a 4-level system here by which you get excitation from level 1 to 4, excitation from level 1 to 4. Then you have an interdefect relaxation from 4 to 3. And now you are in this level here. And then you get recombination between level 3 and 2. You get recombination that is the stimulated recombination between level 3 and 2, and then you have the relaxation back of the defect to the ground states, and so you get the relaxation back to this state here. And this explains the fact that the absorption is spectrally separated from the gain. Good. But this is not the only application interesting for the silicon nanocrystal, not only the gain. So I want to show you a few other kind of application. The first one, since I saw today a few papers on photovoltaics, I want to show you what we can do with silicon nanocrystal in order to improve silicon photovoltaics. So one of the problem with silicon photovoltaics is the fact that we do consume a lot of sun power in internal relaxation, so in heating the cell. So here the idea is to use the silicon nanocrystal to improve the efficiency of the silicon solar cell. And to do that, what we want to do is that we want to take high energy photons and convert those high energy photons in low energy photons in such a way that the energy difference is not wasted in heat of the silicon itself. So to do that, essentially we use the fact that in silicon nanocrystal the absorption is effective in the blue and the emission is in the red. So we want to transfer photons from the blue to the red. And the reason is very simple, because in silicon, if you absorb blue photons, those blue photons are near the surface where defects exist, and so most of the electron hole pairs do the recombine on the surface. And so the efficiency of the silicon cell is lower in the blue than in the red. In the red, you do excite more deep in the silicon where less defects are there, and so you can effectively get a current from those electron hole pairs. And so this is what we want to do. Here is what a first experiment that we did. So we take a piece of silicon nanocrystal, we put those pieces of nanocrystal on top of a cell, and then we look how the solar spectrum is modified, how the solar spectrum seen by the cell is modified by the presence of the silicon nanocrystal. So actually what we did was that we shine a sunlight to the silicon nanocrystal, and then we look at how the cell see this sunlight. And so the green line is the solar spectrum observed by the cell without the silicon nanocrystal. And then we have the red line, that is the spectrum observed by the cell when the nanocrystal do not emit the light. And here you do see a change. You see the green and the red is different. And the reason why the green and the red is different is because the nanocrystal have a different refractive index than the silicon. So you have an effect that is called an anti-reflection coating effect. So you do reduce, by controlling the thickness of the nanocrystal, you do reduce the reflectivity of the silicon cell. But then, if you add now the fact that the nanocrystal can emit light, they do emit light in the red, and so you now see the blue line here. And so you see that more light is coming to the cell in the region where the silicon internal efficiency is larger. And so in this way you can hope to increase the quantum efficiency in the cell. Actually those are calculations, and in this calculation we did the hypothesis that of all the light absorbed by the silicon nanocrystal, only 10% is re-emitted. So here we are assuming that the nanocrystal have 10% of efficiency in the emission. So this is the cell. So here we did also an experiment. So this is a commercial cell. Is slightly different from what you are used to see, because all the contacts here are on the back of the cell. And so on the front surface of the cell, so this is called a back contact solar cell. So on the front of the cell you have only a texturing in order to trap the light, so to reduce the reflection from the cell, but all the contacts you have on the back, so no shadowing from the top, from the metal lines on the solar cell. So this one is a state-of-the-art solar cell in production, and what we did was to put on top of this cell a layer of silicon nanocrystal. Here is a photo of the cell on the back side of the cell. And then we look and we compare a cell with a nanocrystal with a cell without the nanocrystal, but with an anti-reflection coating made by silicon nitride. And those are the results. So here is the open circuit voltage, and you see that the presence of the nanocrystal, what is very important, so the presence of the nanocrystal do not change the open circuit voltage, which means that the surface passivation is essentially the same with and without the nanocrystal. But what is interesting is the fact that the short circuit current, here is the short circuit current density, is increased when the nanocrystal are deposited on top of the cell. And so now if you multiply this by that, so you get that the overall efficiency of the cell has been improved. Here is the internal quantum efficiency versus the wavelength. And what you do see here is the fact that the internal quantum efficiency is actually improved for solar light that is in the blue region, where the nanocrystal play the role to shift the light to the red. So actually, the starting hypothesis has been verified by this fact. However, we were puzzled by the fact that actually the nanocrystal could affect the interface quality of the cell. So we repeated an experiment. We did another experiment where the nanocrystal now are not placed on top of the cell, but are placed on a covered quartz plate that we put on top of the cell. So we physically separate the nanocrystal from the cell. And so in this way, in all the experiments, we use the very same solar cell. So in this way, we aim to look whether the effect is simply due to the fact that the nanocrystal passivated better the cell or not. We do separate, so no longer passivation effect on the cell. And then we fill the gap between the nanocrystal and the cell with a different liquid. And here is a very physical aspect, very important physical point. And what we do observe was the fact that the short circuit enhancement for the nanocrystal is larger than 1 only in a very specific case. And this case is the case when we do put here on the spacing layer a liquid that has a refractive index larger than the one of the nanocrystal. Okay? And the physics, the reason for that is simply the standard Purcell effect. So the Fermi, the probability to get photon emission depends on the material, but it depends also on the photon mode density of states. And if you change the refractive index, you change the photon mode density of states. And so photons tend to go where the refractive index is larger. And so if you put a dipole in air, you get the emission as the typical emission of a dipole. From our point of view, since the dipoles are, the nanocrystal are more or less randomly oriented, so we get the same intensity of light emitted to the up region as well as in the bottom region. But now if we change the refractive index of the bottom region where the cell is, so we can increase the quantity of light that is sucked by the bottom, the quantity of light that is emitted towards the high refractive index region. And what you see here is indeed that. So this is vacuum, n equal 1. Here is a liquid, Griselor, for example, n equal 1.5. And you see that the light is preferentially emitted to the low. And if you increase the refractive index, you get that more and more light is emitted to the region where the cell is. And indeed, if now you compare the result, the experimental results, with what we have observed, you indeed see that most of the light is emitted to the silicon because of the high refractive index of silicon. So here is an example of how, by using silicon nanocrystal, it is impossible to get 1% conversion efficiency improvement in a commercial silicon cell. I want to show you another example, which is an example associated to the way to get light-emitting diodes by using silicon nanocrystal. So here the problem is the fact that, as I said to you before, so we do have that the nanocrystal form in silicon oxide. But as you know, in microelectronics, silicon oxide is used as the gate oxide, so it's used as an insulator, which means that no current flows through the silicon oxide. And so here the question is, how can we electrically pump the nanocrystal if the nanocrystal are in an insulator? And this is a big issue, because if we want to make anything that is valuable, so we have to have something that can be electrically excited, because otherwise we do something that is good for publishing but not to use. So here the problem is, how is possible to get electrical injection? So the only way to do is that we have to use the tunneling effect. So we have to use a quantum mechanical effect. Here is an example of a wafers where we have made a few of those silicon nanocrystal LEDs, various geometries, and then the experiment is very simple. So we use a needle just to contact the top surface of the LED, and then the back contact is on the bottom of the wafers, and then we collect the light by using an optical fiber. So this is a plastic fiber, so it's a very simple experiment. And then we look at how much light we can get. So if we want to use tunnel injection, so what we have to do is that we have to go through the oxide. And here we have two possibilities. So the first one is in the case where we have a thick oxide, so we bend, we apply an electric field, so we tilt the bands, and so then we get an injection that is going through the oxide, so we inject the carriers into the oxide, and then those energetic carriers impact the nanocrystal, and then by impact excitation they do excite an electron hole pairs from which we get the emission of a photon. So this is the first approach that is called the Fowler-Nordheim tunneling, and the excitation mechanism is called the impact excitation. The second possibility is that to make a very thin oxide layer so that we can have a direct tunneling of electrons through the oxide layer into the nanocrystal. But in this case, in order to have a photon emission, so we need to tunnel in both the electron as well as the holes. So we have to inject in the nanocrystal both electrons and holes. So this one is luminescence emitted by unipolar excitation, meaning that it's enough to have an electron current. Here is a luminescence caused by bipolar excitation, meaning that we need to have electron as well as holes. The problem with unipolar excitation is the fact that most of the current is going through shunt paths that form in the substoichiometric oxide. And only a few of them have a probability to impact the nanocrystal. So that means that by using this technique, so the quantum efficiency, the external efficiency of the LED will be very small. On the other hand, bipolar injection could provide very strong electroluminescence. So now the issue here is how can we manage the fabrication of the device in order to get bipolar injection? So the idea we had was to move from a single layer of randomly dispersed nanocrystal to a multi-layer of silicon nanocrystal. And the reason why we want to have the multi-layer is because now the electron current is forced to go through the layer of the nanocrystal. But here the issue is that we need to control the thickness of the silicon oxide between the different silicon nanocrystal at the nanometer scale. So this is from the point of view of the fabrication is a very critical approach. So here are an example of the LEDs that we have fabricated. So this is a typical MOS structure, metal oxide semiconductor, where in the gate, in the oxide, we have fabricated a multi-layer silicon nanocrystal structure. And now then we do contact, and then we force electrons to move from the N-type contact into the multilayer, and holes from the P-type substrate into the multilayer. What you see here is a SEM image where you see that the gate oxide is only 50 nanometer thick, and the white lines are the silicon oxide, very thin, very accurately controlled tunnel oxide in the film. So here is the result. So these are the IV characteristics, so current versus the applied electric fields for the single layer and for the multi-layer. And what you notice here is the fact that you get less injection in the multi-layer than in the single layer. But this is not bad. This is good. So that means that here you have huge shunt paths that for a very weak applied electric field cause the injection of a large current. And so now if we block and we look at the current level, so at the electric field value that achieve the same current for the multi-layer as well as the single layer, and then we look at the electroluminescence coming out, so we do see that the electroluminescence in the case of the single layer is much smaller than the electroluminescence that we get for the multi-layer at the same injected current density. So that means that in the multilayer, we are able to excite more efficiently the nanocrystal. So these are the IV characteristics, and the dots, the points are the electroluminescence data. What you observe here is the fact that you get electroluminescence for very low gate voltage, so you apply a very small gate voltage. And what you also observe is the kind of accuracy that you need in the grow process. So you have to make multi-layers of 2 nanometer silicon oxide and 3 nanometer silicon nanocrystal. But then we decide to play a little bit more with band gap engineering, with the control on the size, in order to improve even more the efficiency of the LED. And the idea is the following. So since it's easy to inject into large nanocrystal, so we put the large nanocrystal towards the contact. But then we get a much larger quantum efficiency in the small nanocrystal. So in the central region, we put the small nanocrystal. So we produce a graded gap active layer, large nanocrystal to the contacts, and small nanocrystal in the center of the layer. And here is the result. So this is the luminescence when we have a periodic sequence of multilayer. And this is the luminescence that we get when we have this graded energy gap system, much stronger than here. That's good. Are we happy? Unfortunately not. Because now if we convert the electroluminescence intensity into a power efficiency, what we see here is that the power efficiency, despite our effort, is still lower than 1%. So in this example, it's 0.2. So here is a silicon nanocrystal LED, few of thousands of them on a CMOS wafer. We turn on the light, so we get some visible light, orange, perfect, coming from the nanocrystal. However, unfortunately, the power efficiency is low, 0.2%. So this means that actually the nanocrystals are very interesting material, but are not good for LEDs. Because 3.5 LEDs, so they have a power efficiency 30–50%. So these are not comparable. So what can we do with those nanocrystals? And so here is an example of an application that we are developing, and actually we are spinning out a company on that, and it's based on the use of the nanocrystal to make a quantum random number generator. Why do we do that? Because nowadays, so all of us are concerned with the security of our data. So we do want that our data should be preserved, should be secure. We do not want that the other can have information about what we are exchanging. So in September, there was an experiment done by some Canadian scientists that remotely were able to control a Chrysler in New York. And this is an issue. So can you imagine that you are driving and then someone from Toronto decide whether to stop your car or not? So this is a real concern. So what we really need, so we need a system that is not expensive, that can provide a cryptographic key in order to encode our data so that the other cannot read. The other cannot have access to what we have in our car. And this is what we are, the market that we are looking at. So random numbers can be used in cryptography, computer simulation, statistical sampling. And the problem is that we want to use quantum effects because quantum physics is not a deterministic physics. So in quantum physics, even though we start from a very similar initial state, the system evolves in an unpredictable way. We only know the probability to go to the left and the probability to go to the right. But we are not certain whether we go to the right or whether we go to the left. Classical physics, yes. If we know everything, so then we can predict where the system will evolve. Quantum physics, not. And so we want to use a quantum source of randomness. And in our case, the quantum source of randomness is spontaneous emission. So this is very simple. We use our nanocrystal. And now the problem that the power efficiency is not large is no longer a problem, because what we did is simply we look at the time when the nanocrystal emits a photon. So we do look the arrival time of the photon by using, by using a single photon counter, and then we acquire the data so that we generate the random bit stream here. So first of all, we look at and we control that emission follow the Poisson distribution. So this is actually a spontaneous emission process. And then by knowing the Poisson distribution, we can know the time that we have to wait to get statistically, probabilistically, 50% probability to have a photon. So we use this time, and then we start to acquire our photons. And here is the result. So this is the random numbers that are generated. And so we can have the arrival or not the arrival of the photon. And so this is the probability to get 0 or 1. And what you see here is that you get that as a function of time, this probability is 50%. Okay? So very good random numbers generated without any post-processing. So we look at several tests that are available. So all the tests pass. And so we get these tests that are passed without any post-processing. Everything was good. But then we enlarge the time frame, we enlarge the observation time. And what we do observe was that the time after a while, so after 500 seconds, so then the probability start to get smaller than 0.5. So here the probability to get the 0 is larger than the 1 to get 1. And this is not good because this is not a good quantum random number generator. And so we look at the reason for the failure. And so here is the electroluminescence as a function of time or for our LED on a day. And what you see is that the variation in the electroluminescence is in the few per mil. Very stable, few per mil, but not yet enough for our quantum random numbers. And the reason is the variation of the temperature in the room. So we did some processings, we did some trick in order to get in a proper way the photons, and this is the result. So this is the a scan in the temperature. So you see that when you change the temperature of the photon source, you get a lower electroluminescence efficiency. But in the way we use to get to extract the data, we see that the probability is still 50%. So this is perfect. So now we can pass and we can try to integrate the device. So the first step was to put the LED on top of the SPAD detector. So this is what we did. So here is the SPAD and here is the LED. Everything worked. So now you can integrate the two together. So this is the way we use to integrate the two together. And then we have our device that we are trying to sell. So since the time is already gone, so I have no time to talk to you about nonlinear effect. So I want to move directly to the conclusion. And so these are my conclusions. So I hope to have convinced you that nanocrystal can enable new functionalities in silicon photonics, actually not for lasing, not for LEDs. So in silicon photonics, the light source is still 3-5 semiconductor. But there are other applications that are possible. Photovoltaics, quantum random number generators, chromophore in bioapplication, and many other. So if you are interested to know more, you can look at those two books, which we recently edited. And I want to thank the people in my lab, as well the different sponsors, European Commission, local government, SPIE, to let me to come here. And then I would like to thank you for your attention.